Okay, so as those of you who are doing divisionals are aware, it is tomorrow. So good luck to everyone who's doing that. And in this workshop, it's really up to like people here. We'll just be going over like problems from, so looking at last year's divisionals. So if you go to our website, CPM Stock website here, at the bottom, we have a problem sheet for this week. If you click on that, it opens up divisional div 2 from last year. And so we're looking at problems from there. In terms of the difficulty we go through, we're going to kind of go through them in a roughly difficulty order, but based on what the people here want, we'll go faster or slower. We'll go over more easier problems or more harder problems, depending really on what you want. To start off with, we're going to look at problem B first, which is not problem B. Sorry, what problem are we going to look at? Yes, problem B. My bad. Yes, problem B. So problem B, biggest integer. So in this problem, we have a number that we want to make bigger. And Annabelle does this by taking a digit and inserting it somewhere into the original number. So we have a number like 7, 8, 5, 3. And we want to insert the number 6 into this to make it the biggest we can. And this is one of the easier problems in the contest. And in this case, for example, we have 7, 8, 5, 3. If we inserted a 6 at the start, we would get 7, 6, 7, 8, 5, 3. If we inserted it in the second place, we'd get 7, 6, 8, 5, 3. If we inserted it in the third place, we'd get 7, 8, 6, 5, 3. The other options are 7, 8, 5, 6, 3, and finally 7, 8, 5, 3, 6. And the biggest one is the middle one here, 7, 8, 6, 5, 3. That's the biggest of all of these. Obviously, it's on slots of 6, it's smaller. Then knock out this one and yeah, knock out these ones. The middle one is the biggest. So in the case of this problem, though, the number that you get given can be very large. So the number can be up to 10 to the 200,000. So you're given a number potentially with a lot of digits, 200,000 of them, and one single digit D, which is the one you're inserting, and you want to output the biggest number you can make. So here is the first sample input. We just went over that one. In this second case, we just add the one anywhere we want. In this final case, we want to add our new 9 to the start to make the biggest number we can. So I guess any thoughts on how we can go about this? I guess what position do we want to insert the number in? Give everyone a minute or 30 seconds or a minute to say anything in the chat or unmute. If not, I'll explain the idea. Hopefully it's not too difficult. So I think you want to make the number as big as possible. And so from there, you just want to like insert it in the place that will do that. So if it's a 9, you want to insert it at the start. What about if it's an 8? Well, you never want to put an 8 before a 9. Like the number starts with a 9, you don't want to put an 8 before it because then you'll be making the number smaller. But if you have a 7, you want to put an 8 before a 7. So in general, if you have some number like 5, you want to put 5 before either a 4, a 3, a 2, or a 1, or a 0 even. But you want to put a 5 after a 9, an 8, a 7, and a 6. So you start with your new number and you loop through this old number until you find a value that is, loop through the original number, sorry, until you find a value that is smaller than the number they give you. So loop through until we see like 7, 8, and then finally 5 is less than 6. And so stick to 6 before the 5. because that will guarantee that the number is bigger. In the second case, we put the 1 anywhere at the end. And in this case here, well, the first number, or 1, is smaller than 9, so it's not than 1 at the 9 at the start. So that's this problem, and it's one of the certainly easier problems in the contest. So generally, divisional round will have quite a few easier problems, like this one here, which isn't too bad. And also, a problem like this shouldn't take too long to code. So I'm just going to share my screen and quickly code this one up. Here we go. So I'm going to use C++, but if you use other language, that's good too. So we're going to use C standard IO. We're going to use C strings. So that's just an array of chars. So we're going to store our word as an array of characters because that's the easiest way of going about it. The number they give you is up to 2 to the power of 200,000. No, sorry, 10 to the power of 200,000. That is way too big to store in any, like even a long can only store up to about 2 to the 63. And this number is so much bigger than that. So we need to store it as a string, which is actually good for our purposes. So we have the D and also the number, and up to 200,000 long. So we're going to scan in our string D and also our number. So scan in D and the string, and then get the length of the string. And then let's just loop through until we find a value smaller than. So for int I, if the value is smaller than it, so if the value here, if that is smaller than D, and notice that even though we're comparing characters here, because the order of characters, they're ordered, so in ASCII, like 0 comes before 1 in the character ordering. So this will be fine to compare the integer version of the characters. So just do that comparison. If that's true, then we want to insert D into the string. So insert D just before position I. So let's print everything before position I. So for everything before position I, we're gonna print that character. We're then gonna print our D here, and then we're gonna print everything afterwards. And then we're gonna print a new line at the end just to end our line, and then we're gonna return 0 to end our main function here. So this will find the first place where the value is smaller than our D, and they'll just print everything. So we compile this code using some useful compile flags. The string function is in C string. That just gets the length of the string. It's in C string, which is also known as string.h if you've done C. This might have been covered in some of the C courses. So here, let's just have our input file. So the first input is this. So run our code on this input. It outputs 78653, which is correct. In this case here, it outputs nothing in this case, which is a bit of a problem. It should output something. Now, if we look at our code, we'll see that any thoughts into what's going wrong in this code? Why is it outputting nothing? Well, it's outputting nothing because this if statement here is never being run. So something's going wrong, that if statement is never being run. And that's because all our values here are ones. And because all our values are ones, then this 1 is never smaller than any of these ones. And in this case, we can just pop up 1 on the end like this. So in the case where this statement never happens, at the end, we can just print our string followed by the character D. And so now in this case, it'll print out the correct answer. In our final case, we want to put the 9 at the very start, and our code does that. So that's the very first problem. And as you can see, it's fairly easy. And in fact, this isn't even the easiest problem in this contest. So there are a few problems of this difficulty level. So if there aren't any questions about that, I'll hand over to Isaiah, who will run the next problem.
Yep. Yeah, I guess we'll just quickly ask how people found the difficulty of that one, since might as well do problems that match the difficulty of what people want. So if people found that, if people want it to be, like, I guess, slightly harder than that, put your thumbs up, because I guess that's where we're headed, if by default.
Yeah, if you think this is way too easy and go to like much harder problems, let us know. Otherwise, we'll just go do a little bit harder, then a little bit harder, and just work our way up for the rest of the time.
Yep.
Which problem do you want to do then?
Do G. Okay. So kind of a long statement, so I'll just try and explain the statement through the samples. So let's give it 10. It's pretty big. It's fine. So yeah, so in this problem, you're given like an array of numbers. So up to 200,000 numbers, each between 1 and 1 billion. And you're going to want to order them in some optimal way. So you're going to want to find some optimal ordering of them. And the ordering is measured in this really weird way. So what you do is you take each pair of consecutive terms. I guess could you zoom in a bit, just because I can, on the sample. Yeah, okay. I guess I'll just write it out. So like the quality of the permutation is measured in this really weird way. So you take each adjacent pair, and if the second one is bigger than the first one, then you add 4 gold, or you add the difference in gold coins. And if it's smaller, you add the difference in silver coins. So in this case, since this one's bigger, you add 4 gold coins. I might be getting this wrong around, but it doesn't matter. And this one's bigger than this, so you get 2 gold coins. And in the last one, the second one's bigger than the first one, so you get 5 gold coins. So that wasn't very interesting. So the point of the problem is that you can actually choose which order you put them in. So for example, in this one, you could put them in the order 15, 22, 11, 17. In this case, so that one's the same. You get 7 gold coins there in the first one. And this one, the second one's smaller now. So you'll get 11 silver coins. And the last one, you'll get gold coins, and you get 6 gold coins. And so that's how you get coins. And the way that you actually score your permutation is the difference between the number of gold coins and silver coins. It might be framed slightly differently in the problem. Yeah, in the problem, it's framed as like you cash in your gold and silver coins, and however many you have left at the end, that's your score, and you want to minimize your score. So you want to minimize the difference between your gold and silver coins. Your gold coins are the differences between terms that are bigger than the last one, and the silver coins are the differences between values that are smaller than the last one. So does that make sense? I know it's kind of convoluted. I just tried to condense it down to its essentials. If the problem statement makes sense, could you put a thumbs up? Otherwise, yeah, the link to the sheet is, Angus just posted it, so you should be able to read it if that wasn't clear. Once it's clear, can you raise your hand on Zoom, just until most people have understood the problem, then I can continue. I guess in the meantime, I'll explain the second sample. I'll explain the first sample in full. So in this case, if we take the difference between the gold and silver coins, we got 13 gold in total and 11 silver. And so our total wastage is the absolute difference between these two numbers, which is 2. And in this case, that's the minimum you can possibly get. So the output's 2. So that's why the answer is 2 here. You can see, you can, I guess, try every single permutation. And if you do the same procedure, you'll get something that's bigger than or equal to 2. So for the second sample, I guess there's only 3 arrangements, so it's easy to check them all. So 1, 2, 2, you'll get a gold coin from this, and you'll get 0 gold from this one, so that just nothing happens. So in that case, your cost is 1 because the difference between gold and silver is 1. If you put the 1 in the middle, so 2, 1, 2, then this one you'll get 1 silver coin because it decreases by 1, and this one you get 1 gold coin because it increases by 1. And so the absolute difference is 0, and obviously you can't do any better than 0, so that's the answer. But also, if you did the last case, which was 2, 2, 1, then it's symmetric to the first case, so you would get a score of 1. Any more samples? Yeah. Okay, so that one, the order is basically fixed. You can either do it that way, you can do the other way, and in either case, the absolute difference is 99999. That's very interesting. Okay, so just again, hopefully either you've been listening to me or you've read the problem yourself. But if it's clear what the problem is asking, can you put your hand up on Zoom? Otherwise, say something in chat if it's unclear. And if you can't raise your hand because of your Zoom version or something, then say that as well. So no one's saying anything or putting their hands, so I don't really know if people understand the problem, but I'm assuming you do because you're not saying anything. In which case, if there are any observations that people have about the problem or any solution ideas, feel free to put them in the chat or say them at this stage. All right, so with this problem, it seems kind of scary because your choices are to like commute a whole list. So in general, like if you're trying to optimize some property about commuting a list, then it's going to be really hard unless there's some nice property we can exploit. In this case, it's quite a complicated metric for how good a permutation is. But there is actually, you can actually simplify it quite a lot, so it becomes solvable. So I guess if you observe the first sample enough, if you just play around with it, or any small case, then you'll see that since you're taking consecutive differences, that's kind of nice. So I guess it's not, yeah, I guess the easiest way to see it is to just play around with a few cases. But you can kind of see that, so your silver is going to be the sum of negative differences, and your gold is going to be the sum of positive differences. And so, your negative silver is going to be your sum of difference. So your negative silver I guess I might as well say it, your gold minus your silver is going to be the sum of differences in the correct direction. So what that means is gold is always the difference in this direction. So it's second minus first, or second minus first. And silver is always in the other direction. So it's first minus second. So if you take all your gold minus silver, then what you're going to get is you're going to get all your differences in the correct direction. So gold minus silver, which I'll do in blue, it's going to be that minus that, minus that, minus that. And add it all together. And once you see that, you can probably tell that if you add the difference, if you take the differences of all of these and add them together, then you get the total difference between the first and the last number. And you remember that the metric that we're actually trying to solve for is minimizing the absolute value of this. So that is actually equal to the first minus last number, or the last number minus the first number. So I don't know how the problem states it, but I can guess I can write Pn minus P1 if that's our if P is our permutation. And then, so we're just trying to minimize that difference. And so to do that, all we're doing is finding the difference. We're just trying to find our first element and last element such that the difference, or the absolute value of the difference, is minimized. So G minus S is Pn minus P1, and so the absolute difference is the absolute difference of that. And so we've reduced the problem to just finding the smallest difference between two numbers, between any two numbers in the array. Yeah, so does that reduction make sense? I don't really know how people are thinking because I haven't heard much back from you, but does that reduction to this make sense? I know there are a few steps along the way. And if that reduction makes sense, how would we solve that problem? So we've reduced the problem to finding the smallest difference between two elements of this. Does anyone want to tell me how to do that? How to finish it off, or ask for any clarifications on how we got there? Okay. Yeah. So what we're trying to do is find two elements such as their differences, two distinct elements, or not necessarily distinct numbers, but distinct indices, I guess, in the input array. So the easiest way to do this, or there's probably many ways you can do this, and you can probably Google how to do it, but an easy way to do it is to just sort the list of numbers. So the first step is sort the list of numbers. So in the first case, they're already sorted, I think. Yeah, they're already sorted. So, and once you've sorted the list of numbers, the difference between the smallest two is just going to be the difference between any two adjacent elements. And I won't prove that because it's pretty obvious. So in this case, the difference between the first two is 4, the second two is 2, and the last two is 5. And yeah, so you can check. So our answer is 2, because that's the smallest difference between any two elements in this sorted array. Yeah. And we remember at the beginning, if you can remember at the beginning, I had my array starting with 15, ending in 17, or maybe the other way around. So it was possible to get 2. In the second case, if we sort 2, 1, 2, we get 1, 2, 2. We compare adjacent elements. The difference is 1 there. So that one's 1, that one's 0. And so our answer is 0, because 0 is the smallest difference between any two adjacent elements. And the last case, it was 1 in a million. In that case, it's the sorted order is 1 in a million, and the difference is going to be, the only difference is going to be 99999. So that's our answer. Yeah. So yeah, I guess in summary for this problem, feel free to ask questions at this point, but in summary for this problem, we reduce the problem to finding the smallest difference between any two numbers in the array. And to find that number, we sort the array and find the smallest difference between any two adjacent elements. So I guess we can wait for a minute if anyone has any questions. Otherwise, this can talk about another problem. I guess we'll just wait for a minute. Yeah.
Have you shown them where the problems are from? Problem for fun and like how to submit and things like that?
I guess we can go through that. Although the problem solve, you can view the link on our website here. You can submit on Prog for Fun. I guess I can quickly go over that while now. Let me just clear the annotations.
Yep.
So Prog for Fun. What is this? Prog for Fun. I'll send a link. Where is here? So there's a link here. If you then sign into this, you have to make an account. Shouldn't be too hard. You should all know how to make accounts and stuff. Then you can just click on the archive here. The contest we're doing, as it says here, is the 2020 Divisionals Division 2. So if we go to ICPC contests and to 2020 Divisionals Division 2, and it's just like it's just set up as a Moodle quiz. You continue here, and you can submit to any of the problems. You can also see the scoreboard. So problem B, the first one we did, almost everyone in the contest solved it. Problem G we just did was less solved, but still one of the higher solved problems in this division. Noticing that there were 2 divisions last year, so this was the lower division for open competition, whereas Div 1 was the people going for World Finals. It's different this year. We just have 1 divisionals. Last year was an odd year because of COVID. I mean, there's still COVID, but it's going back to a more normal format this year. So submitting, you can just like literally put your code in here and submit and check, and that should mark your code for you. We're not focusing on that too much here for interest of time, but if you want to solve in your own time, they have so many past problems for like every year, essentially going back 5 years or so. And they also have like assorted they have Anzac rounds, and it's from the University of Canterbury. And so they have the New Zealand contests too. Okay. So on that note, we're going to move on to problem H. I can't see the tabs because of Zoom getting in the way. It's this one. Where is it? Oh, it's this. Oh, we're back on it. All right. So Zoom was being. Okay, here we are. Problem H here. So again, you can get to it from our website, which has been linked in the chat a few times, and click here. Here we go, back. So in this problem, you have 2 students, and both of them are asked what their favorite numbers are, which we'll call X and Y. So you're given 2 numbers, X and Y. Now the teacher wants to buy some paper, which has a width of, so a rectangular piece of paper whose area is their favorite number. So I get a paper with area X and a piece of paper with area Y. Now, there are some limitations. First of all, the width of the paper has to be 2, 3, 4, etc. So an integer, not 1. So 2, 3, 4, 5, 6, 7, 8, 9 upwards. Just notably, it can't be 1. And it must have an integer height. So if X was 18, it could be 2 by 9, 3 by 6, 4 by nothing. That doesn't work. It's not integer. 6 by 3, 2 by 9, and 1 by 18. These are the options. Notice how we can't have a width of 1. We can have a length of 1. We can have 1 by 18. But it does this for both pieces of paper. So you can buy them separately like this. But there's a second option. You can instead buy one piece of paper, which has the same constraints. So it has to be a width of 2, 3, 4, etc., and an integer length. But then he can cut it into 2 halves. And when he cuts into 2 halves, he has to cut it along an integer coordinate. So you can buy one piece of paper and do one cut, either a horizontal cut or a vertical cut. And that vertical cut or horizontal cut must cut the paper into two pieces which have integer side lengths too. So he could buy a 3x10 piece of paper and cut it into a 3x4 and a 3x6 to make one of size 12, one of size 18, for example. Now, the cost of buying a piece of paper is its width. Doesn't matter what the length is, the cost is the width. And so to buy 18, for example, the cheapest one is 2x9. So smaller widths are better, no matter what the height is. So the question is, what is the cheapest way to make one rectangular card of size X and one of size Y? We have a few examples here, 10 and 25. Now, it goes over a few options here. So one option is to buy, we can buy a 2x5 piece of paper and also a 5x5 piece of paper. The cost will be 7. Alternatively, we can instead buy one 5x7 piece of paper that costs $5, and we then cut that piece of paper into one of 5x2 and one of 5x5, and that gives us the two pieces of paper we want with area 10 and 25 and costs us only 5. So that is the cheapest way to go about that one. In this second case here, we have 17, 12, and 17. One option is for the 12, we can buy 2 times 6 for a cost of 2. That's the cheapest one. And for 17, we can't buy 1x17, but 17, we can buy 17 by 1 for a total cost of 17 plus 2 equals 19. Another option would be to buy a piece of paper that is 29 by 1 and cut it into 2 pieces of paper with one is 12 by 1 and one is 17 by 1. This is certainly cost 29 is certainly much more expensive. So the first option was a lot better than that. Finally, we have a third sample input case. In this case, we have 10 and 15. In this case, we could buy 2x5 and 3x5 for a cost of total 2 or 3 is 5. Alternatively, we could buy a 5x5 piece of paper and cut it into a 2x5 and a 3x5. They both cost 5. They cost the same amount. So both cases cost 5, and so they're equally as good. And yes, so that is this problem here. Again, as before, just chime up if this doesn't make sense. And if you want to read it on your own computer, it's linked to down here. So some important note that I didn't mention, but the constraints on X and Y are anywhere from 2 up to 10 to the power of 10, which is 10 billion, which is a very large number. And so they have a nice little note here, which they may have in divisionals, they may not, but it's just a nice note here, a bit of advice, which is your algorithm must be fast enough and correct in every case. We know that already. In this problem, X and Y up to 10 to the power of 10. And so doing even a simple loop from 0 to X will be too slow, because in general, you can somewhere between 10 to the 7 and 10 to the 8, which is 10 million to 100 million, is how many operations you can expect a computer to do in a second. A reasonable speed computer, like the judging machines that we use for these contests. So a reasonable judging computer can do approximately 10 million to 100 million operations in a second. The time limit is 5 seconds. So a reasonable computer could then do somewhere from 50 million to 500 million operations in 5 seconds. Now, the upper bound of that, which is 500 million, is well below 10 billion, like 20 times smaller. And so, yeah, as I said, even a simple for loop would be too slow. And so we need to do something smart to solve this problem for these very big constraints. However, when solving a problem like this, can be useful to first come up with a slower algorithm and then try to improve the algorithm so that it works on bigger cases. So that's one thing we might want to do. We want to first solve on smaller cases. And then if our solution is too slow, we then try to improve it for bigger cases. The second thing we like to do in problems is problems can be hard. So when solving a problem, we can first simplify down the problem to a simpler one and try and solve the simpler problem first. So in this case, we have two options. The first option is we buy the paper separately. So we buy X and Y separately. And option two is we buy them together. Now, we might want to consider these two cases separately. First, consider what is the best price if we buy them separately. Then what is the best price if we buy them together? And then take the best price out of those two. So let's first consider the separately case. So what's it cost if we buy X and Y separately? Because that is a nice way to start. And the reason why I chose this one first is because it kind of seems easier, because we can then split it up even more. We can reduce it to, given just X, the cheapest cost to buy X. Why is that? Because we can run this for X and Y and add them together. So given X, what is the cheapest cost to buy X? Now, I think it is worth thinking about this. So I'll give about 30 seconds, although we're not, I'll chime in if we don't hear anything, but it is worth, if you can, to certainly chime in. But I'll give you 30 seconds or so until I'll give some ideas. Find the smallest prime that's a multiple of X. So we have X. Want to find the smallest prime that's a multiple of X. Now, by multiple, I think, do you mean divisor of X? Because divisible X, yeah. Because in fact, both of those, X is divisible by the prime number, yeah. Because obviously, yeah. Well, yeah. Yes, so we want to find the smallest prime that divides X. And so why is that? Well, we want to make X, we want to make the width as small as possible, because we want to make something of area X. We want some sort of rectangle. We want to minimize the width. So we want to have some sort of rectangle that has A and B, where A times B equals X, and A is as small as possible. And so, in fact, we can say we want these are going to be factors of X. So we want the smallest non-1 factor of X. And in fact, these are the same thing, because the smallest factor will be a prime number. If you don't understand why that's the case, don't worry too much. Just maybe have a think about that. It's probably a nice exercise, nice, simple, number theory exercise. But well, the smallest non-1 factor of X, because we want X divided by A to be an integer so that we have integer side links, and we want A to be as small as possible. Yeah, exactly. Dallas wrote it quite nicely there. If it's not a prime, then the number that divides it is also a prime. Yeah. Now, the question is, how do we find the smallest number that divides X? Well, the simplest way is just to loop through. We just loop through all the numbers until we find a prime number. And I think the best way to show that is just like the code for that is very simple. So if we go, what problem is this? This is problem H. Like let's say int smallest factor. I actually need long, so because the numbers can be too big for an int, so we want to find the smallest factor given x. And our code looks like we just loop to every number. If x modulo I is equal to 0, then return I. So what we're doing, we just loop through every number. We check if I divides x, and if I does divide x, we're done. Now, this is all well and good. The main issue is the fact that we're looping potentially all the way up to x. Now, this actually breaks as soon as it can. So this will return once it finds number. So for example, if it's an even number, it'll return very quickly. If it's divisible by 3, it'll return very quickly. And in fact, this function will normally not loop all the way up to x. In what case will this function loop all the way, this for loop all the way up to x? So what values of x give us the worst case performance for this for loop? If x is prime, exactly right. If x is prime, then this is bad. But if x is not prime, yeah, so if x is not prime, so if x is not prime, then x equals a times b for some a and b greater than 1. Now, if x equals a times b, this is a fairly classic disclosing fairly classic idea, but I'll just mention it briefly. Then the minimum of a and b must be less than or equal to the square root of x. Because if a times b are both bigger than the square root x, if a and b are both bigger than the square root of x, then a times b must be bigger than x, which is a contradiction. So if two numbers multiply to give x, one of them must be smaller or equal to the square root of x. And so if x is not prime, then it must have some divisor less than the square root of x. And the square root of 10 to the power of 10 is 10 to the power of 5, which is much more manageable. What we can do is we can loop all the way up to square root of x. So to do that, we go like, we loop while I times I is less than x. So while I is less than or equal to square root of x. And if we don't find anything, we then at the very end, we return x, sorry. So if we go to our main function, let's just write it. We're going to scan in x and we're going to print the smallest factor of x. So we compile this code, same compile flags. It doesn't have to hash include this. So we run this code, we give it like 10, it gives us 2. We give it 17, it gives us 17. So if it's prime, it gives us a prime number. If it's 52, it gives us 2. If it's 83, it gives us that's prime. 87, 3, 85 gives us 5, etc. So it's giving us the smallest factor, which will always be prime. Smallest non-1 factor, obviously. And so to solve this problem, case 1, so the problem we're given x and y, we scan in x and y, and the answer is the smallest factor of x plus the smallest factor of y. And that is case 1. Now that's the first case. The second case, which is a bit more complicated, is, well, what if we want to buy one piece of paper and cut it in half? Because we're allowed to do that. That's our second option in this problem. But remember the rules. If we buy one piece of paper, we have to cut it either like this or like this. So either vertically or horizontally. Draw that like, do one cut along integer coordinates. So if we want to, let's say we want to cut it, let's say we have a width W and a height H, and we want to cut it in half. We have area X, area Y. Then our condition, we want W times H will be equal to X plus Y. But more, because we must cut an integer coordinate. Let's say we cut it at position, we're going to have big H, which is our height, and little h would be where we cut it. So we want the width, assuming we cut it along like vertically like this, we want the width times little h plus the width times big H minus little h. So to clarify, big H is the width, is the height, and little h is the like height of the very top bit. Like this, we want the width times little h. We want the width times little h to be equal to x, and the width times big H minus little h to be equal to y. That's kind of that's our condition we need to satisfy. If we want to cut a piece of paper and cut it vertically like this, cut it horizontally like this. Now, in the case where we do cut it horizontally, the cost then of buying a piece of paper is W. Now, what W should we find that minimizes the cost of doing this, of doing one cut horizontally? What's our condition on W? Divide X and Y, GCD. You want the smallest. Yeah. So you want the smallest common like divisor that's greater than 1. So you want like the smallest common factor that isn't 1. And so, well, what's one way we can find the smallest common divisor? There are probably a few ways of doing it. Any thoughts on what that one way of doing it? There are many ways to do it. Well, I guess one way to do it is just first find all the factors of X. So find all the factors of X and then check which of these factors are factors of Y and take the smallest one. So smallest non-1 common factor of X and Y. Well, we want to find all the factors of X and Y. So let's just make a vector, which is factors of X. Now to find the factors of X, we can use our square root idea. So we do a similar thing to here. If X divides I, then, well, that means that X is a factor. So factors of X, we're going to add I as a factor, but also X divided by I is also a factor. So we have all the factors of X here in our vector. Yes. And now that we have all the factors, and potentially, well, X could also be a factor of X. Oh, and X is also a factor of X. Sorry, factors of X. Obviously, X is a factor of itself as well. So we're going to put that in there too. because 1 is, well, in this context, 1 is not a factor because we're ignoring 1. But x is a factor. They're all the factors of x. And then we want to find the ones that are in common with y and find the smallest one. So let's have the smallest common factor. Let's just set to like infinity. So 1e18, infinity we'll say, is currently the smallest common factor. Then we just loop through for every common factor, or for every factor of x. So for every factor of x, if it's a factor of y, so if y mod a is 0, so if a is a factor of y, then update this to be the smallest one found so far. Like this. And we hash include algorithm. For the, yeah. So this is, and then we return the smallest common factor. And it'll return infinity, or 118, 10 to the power of 18, if there's no common factor. So let's just, for now, just print out the smallest common factor of x and y. Check it works. So we compile our code again. Here, we're gonna have to hash include vector here. And let's also compile with C++11. Unused variable answer, don't worry about that too much. Let's just clear our screen. Run our code. Yep, I'll get to that in a second. So yeah, like 5 and 10, 5 small common factor, we get like 18 and 24, we get 2. If we get like 7 and 9, then there are no common factors, so it returns this infinity. And we get, what else could we have? 21 and 49, then 7 is the smallest common factor. One thing Dallas said, if you're on an early exit, you can put all the factors, yeah. So the idea is then you could kind of, if you, to find a smallest factor, you could sort all the factors and then loop through till you found one. We can't early exit here because this vector isn't in sorted order. But as Dallas said, if we had 2 vectors where one of them is factors less than square root of x, one of them is factors bigger than the square root of x, then they're kind of implicitly sorted already. And we can do that. So that works too. Either idea works. Okay. So we set our second answer. So let's say answer 2 for now. Our formula from before was, it was just the smallest common factor. That was the answer. The smallest non-1 common factor. So the first case, so we've now considered the case where we buy them separately, the case where we cut horizontally. Our final case is a case where we cut vertically. Width, height. We're going to use notation. We're going to have big H for the height. We'll have big W for this and little w for this one here. So big W is the entire width, little w is the small width here. So we want H times little w to be equal to X, and we want H times big W minus little w to be equal to Y. Now, what condition, and we want the width, and we want big W to be as small as possible. What's our condition on H to ensure that this is true? We want H times little w to be equal to X. We want H times big W minus little w to be equal to Y. And we want W to be as small as possible because that's the cost. Well, we want W to be as small as possible. So we want H to be as big as possible because that's how multiplication works. And so we want H to be as big as possible and H to also be a factor of both X and Y. So we want H to be the GCD of X and Y. If H is the GCD of X and Y, then W is just X divided by H plus Y divided by H. That's big W here, like that. So our final answer, so this is by separately, this is by together, cut horizontally, and finally we have by together, cut vertically. And so I want to find GCD. Now, GCD is actually built into C++ 17 or above, I believe. GCD, I think it's C++ 17. It also underscore GCD exists in older versions of C++, but in fact, I'm just going to code it up so you have a reference for it using Euclid's algorithm. So GCD of A and B. So the algorithm is if B is equal to 0, return A. Otherwise, return the GCD of B, A mod B. I'm not going to prove why this works here. This is covered in like, I think, Math 1081, and you can like Google the algorithm, and you'll see like Google Euclid's algorithm, and it will like there'll be many proofs online. It's also log complexity, order log. The reason why it's order log is that each time you like do this A mod B, it the proof from it is a bit fiddly, but you can show that it reduces like logarithmically in terms of the size each time, or like, yeah. So that's GCD. So we find the big H is GCD of X and Y. Then our third answer we said was X divided by H plus Y divided by H, because that'll give us this big W. And now we just print the smallest of these three answers. So the minimum, the min function takes in two values. So it's like the minimum of, I think you can give it a vector, or you can just do the minimum of like answer 2 and answer 3. That's one way of doing it. I think you can also pass the minimum function like a vector or something. Like this will work. I think it also works if you do like, does this work? This might work. Our code doesn't like it. I'm not sure. But certainly like this case certainly works like this. Okay. If we run our code on some input, oh, it's min elements for a vector. I see. I'm getting Python and C++ confused. So we can do like, oh, doesn't, whatever. Like ans2, ans3. If we give it min element, oh, when you give it beginning end effect, don't we? Yeah, okay. It becomes a bit. I need to give it the dot begin dot end. Okay, that's a bit of a pain. Yeah, okay. I see it's a bit of a pain. Yeah. This way is probably simpler code up. You have to give it a vector and then give it iterators. You can't do it like in place nicely. Okay, we'll do this here. This is a lot nicer way of doing it. So our first input case was 1525. The answer was 5. Second case was 1217. The answer was, 1217. The answer was 19. And 1015. The answer was 5 again. Let's look at my typo case, which was 1517. In this case, what can you do? Why do we get 20 in this case? 3 and 17, right? You just buy them separately. Yep, seems good. Okay. And because the numbers are like, I mean, 15 and 17 are co-prime. So this buy together idea just won't work for those cases. But some cases where it's good to buy together, yeah. So this is this problem. Again, we could submit it. In the interest of time, we'll just trust that it works. But obviously in a contest, you'd submit it. And in a problem with 3 cases here, if your code was to get wrong answer, what I would do is make a case for each of these 3 cases here, and then test your code on them, because yeah, who knows? Maybe one of these is like in a contest, one of these could be bugged, but yes, here is our code, which certainly at least conceptually works. So let me know if there's any questions. Often in like an ICPC contest, there might be one problem in each contest that requires some sort of maths like this. There's normally some sort of problem that requires some sort of number theory, where that number theory is normally like some number of like finding primes or GCD. Like it's not generally like super advanced number theory that will require like heaps of math knowledge, but certainly some knowledge of prime numbers and GCD will help you solve generally one problem per contest, although obviously it varies. But yes, that is this problem complete. I'll hand over to Isaiah and I'll share my screen again with the problems.
Yeah, I can look at problem K. Okay. So this problem is kind of a geometry problem, kind of not really. So given a list of coordinate pairs, so a list of points in the 2D plane, and so I guess how the problem is framed is you can pair up certain pairs of people. So each person can belong to a group, and each group can contain either 1 or 2 people. And you want to group the people into groups of 1 or 2, such that the minimum distance between any 2 people who are not in the same group is maximized. So that's kind of a mouthful, but yeah, you're trying to separate the groups as much as possible, and that means separate any pair of 2 people as much as possible. So I'll do the first sample. So yeah, all the coordinates can be negative, but yeah, so 0, 0 is there, 3, 2 is there, 4, 1 is there. I guess I'll do this. And in this case, what you want to do is group these 2 together. You can see that they're really close to each other, so we can group them. We can't group them all 3 together because that's not allowed. And then this person will just be left on a group by their own. And then we want to find this. So that's the optimal arrangement. I guess you can try the other 2, which would be to group these 2 people and to group these 2 people. And I guess the other one would be to leave everyone alone, but clearly that's not a good idea. And in this case, the maximum distance between any 2, you can check this distance and this distance. This distance will be 3 squared plus 2 squared, or the square root of 3 squared plus 2 squared, which is root 13. And this one will be root 17, root 4 squared plus 1 squared. So the minimum distance between any 2 people is root 13. And so our answer is root 13, because that's the best we could have done. I guess, for example, if we group these 2 people, then these 2 would have been very close. They would have been root 1 squared plus 1 squared apart. And we could have done better than that. We could have gotten a minimum of 13. Okay. Let's quickly run through the other samples as well. So the next one, we have something like 1, 1, 2, 2, 4, 4, and 5, 5. In this case, it's kind of clear that the optimal way to group them will be to group those two together and those two together. And the minimum distance in this case will be between those two. And that was 2, that was 2. And so the minimum distance was root 8. And yeah, so everything you can kind of see is going to be the square root of an integer from the problem. And it even tells you how to calculate it, I guess, kind of, using Pythagoras. And so you just output the square of that. So you just get rid of the square root sum. That one's 8, and that one was 13. Third sample. So hopefully most of you have understood the problem by now, in which case feel free to think about it. But if you haven't, that's why I'm just going to continue explaining the samples. -3. Failed. So in this final case, yeah, I think they're both supposed to be a distance of root 17 away. So both of these are root 17. Might have messed up the maths, but whatever. From my diagram, they look pretty close in distance anyway. And so regardless of how we do the grouping, or not regardless, but I guess I'll just say, so if we group those two people together, then the minimum distance will be there, root 17. If we group those two people together, then the minimum distance will be root 17, but in that for that one. And if we group those two people together, then the minimum distance will be root 17 still. Yeah. And if we group everyone on their own, the minimum distance will still be root 17. So that was kind of an easy case because there wasn't like a small triangle, I guess, which there was in the first one. All right, I'll give people 30 seconds to say any observations they have about the problem or any solution ideas. Any clarifications about the problem, of course, if that wasn't clear. But yeah, hopefully you've had a chance to read the problem yourself and understand it if my explanation wasn't very clear. All right, seems like there are no suggestions, so I'll just carry on. So I think when I run this problem, I can make my pen thinner. That is nice. So when I read this problem, it's kind of like a maximizing the minimum distance idea. So you might think like a binary search thing, since you want to check whether each social distance factor is called in the problem, or minimum distance between any two non-grouped people. I forgot what their sentence was going, but yeah, you want to minimize the maximize the minimum distance between any two non-grouped people. And so you might want to check whether each each minimum distance can be achieved. And you can kind of do that. In fact, that would probably be a working solution, is to binary search over a minimum distance. But how do we know if a minimum distance is valid? Now, in this case, we want everyone who is less than or equal to the minimum distance to be in the same group. And since groups can only contain 2 people, that means that so if we like construct the graph of people who are too close to each other or smaller than or equal to our goal distance, then there can be no like components in the graph that are bigger than 2 people. So that was a lot of words, but if we construct some case, then we can kind of imagine, okay, can we achieve a minimum distance of like this length? This is kind of very visual, but whatever. Can we achieve a minimum distance of that length? And so what we do is we look at every single pair of distances and we connect the nodes if they're smaller than or equal to that distance. So these two are smaller than that distance, these two are smaller than that distance, and no other pairs are smaller than that distance. I don't know, like just pretend that that's how my drawing works. And so in that case, this would be a valid minimum distance because no 2 people are too close. But if we make it a bit bigger, say this big, then now this edge would be included. And let's say that edge there isn't included. So and now we can't actually group people. So if this was our goal minimum distance, then we couldn't actually achieve that because these 2 people are too close and these 2 people are too close. And so we can't actually form a valid grouping because if we wanted the grouping to be valid, then we'd have to have this person in the same group as this person and this group in the same group as this person. And that means they'd all have to be in the same group, but that's impossible because we can only have groups that says 2. So yeah, so that's kind of the intuition behind how you might approach this problem. And so you might think we can binary search and then for each graph that's formed, we do that and that would work. But a simple way of, I guess, ultimately just implementing it in the end, but also I guess you get a slightly better understanding of the problem, would be instead of binary searching, we're kind of just, the only thing that is changing is the distance between people. So what we can do instead is we can just find the distance between every pair of people. And then we go through those distances from smallest to biggest. And whenever we find a distance, we need to group those people. If we don't group those people, then, so I guess it's a greedy algorithm. And so we're going to go through the distances and add them size by size. So I'll just demonstrate it and then I'll explain how it works. Oops. So let's say this is the smallest. I know they're kind of similar, the top and the right one. Let's say that's the smallest distance. So we add them and we add them to a group. That's a group. Then we add this pair. Now they're a group. So that's the second smallest distance between any 2 distinct people. Now the next smallest will be this one. And that caused conflict, as we said, because we kind of figured it in the same group. And so we end it there and we say that our minimum distance is actually that distance there. So our answer is going to be that because these 2 people have to be in different groups. And there's no bigger distance because we sorted them. Okay. The reason that this works, this greedy algorithm works. So suppose that we didn't group 2 people when they're the smallest distance available. The only reason we do that is so they could group with someone else. So say we don't group these 2 people. The only reason we do that is so we can group one of them later on. So say we group this guy later. But then because we did them in order, this distance will be bigger than this distance. So there was no point in doing that because now it's smaller than it had to be, or possibly smaller than it had to be. So instead, we'll just group them as early as we can. So we actually so that's the proof basically. It's not very rigorous, but yeah, along with the binary search idea, you can probably see intuitively why that's true, and probably enough intuition to be very confident that you could implement this. And if you implement it correctly, that you'll have the correct solution. So yeah. So in summary, the solution is find the distance between all pairs of distinct points And that distance can be the squared distance, since that's easier to calculate or easier to handle than the square root thing. Sort them, add them to groups in order. And if you ever have to add someone to a group who's already has a group, then stop and return that distance, because those two people that you're up to will have to be forced to be in a different group because one of them is already in a group. All right. Yeah, just to make it as clear as possible, I'll quickly run through the solution of the samples. Yeah, okay, I'll just roughly go through it. So I think the first sample was shaped something like this. So in this case, we grouped those two. And then the next shortest distance, I don't know which one it was, maybe that one. Yeah, that one was root 13. That this separated two people who were in, and one of them was already in a group. So we had to return this distance, which is 13, root 13. In the next case, we had a bunch of people along a diagonal. We grouped these people, they're the smallest. And this one had to cause conflict. So we returned that distance, which was 2 squared plus 2 squared. And this is the square root of that squared, which was 8. And in the last case, I think it was shaped like that, like an isosceles triangle. So our sort might have returned that one first, say. So we grouped those, and then this one was a conflict. So we returned that distance, which was 17. Cool. Yeah, so I've been talking for a while, so hopefully if there were any issues with understanding that solution, it would have been raised by now. So I actually just implemented this problem. So I'll just share that since, yeah, I won't implement it live because I've already implemented it just then. So yeah, the only reason I'm sharing this is because there's some details around how to implement the sorting that might be useful for some people. Yeah, so you can see my screen. So yeah, it's a very, very short solution, similar to the other problem that I said. Actually, the other problem I think was a very short solution as well, but has some nice observations behind it. So yeah, I'll just go through it. So yeah, a lot of reading input, and I use the same loop to read the input as I did to push all the pairs to a thing. Now, the interesting thing is how we sort. So what we're sorting is pairs of numbers. C++ syntax, it's kind of annoying with pairs compared to say Python, but you have to deal with it. We could implement it in Python. Bit easier in C++, just because comparators is quite nice in C++. But yeah, so we have a list of pairs, which is just the list of each distinct pair of values, and yeah, we don't push them. We don't push like 1, 2, and 2. We don't push them both. The way that loop's set up, we don't do that, mainly because of that. Yeah, so we sort them, and we sort them according to a special rule. And to do that, we pass in the function. So normally, if you just want to sort stuff in ascending order, you do that. But if we pass in like that, then we have a function, and that function has to have this form. And you can look up C++ reference if you want to see the full details on how to set up a comparator. But it can be quite straightforward. In this case, it is. So we pass in 2 pairs because each element here is a pair. And then our comparator should return true if and only if the first number passed in is less than the second number passed in, according to our order. In this case, that just means the distance between the two numbers. So these two are indices. So the distance between those two is less than the distance between the next two. And the distance between two indices or positions in the array is just going to be the difference between the x coordinate squared plus the difference between their y coordinate squared. That's how the comparator works. And so that's all code in that syntax. It's actually fairly easy to remember. So you're just writing a function that returns whether the first one's less than the second one. Yeah, and that's the basic logic as I went through. So if we've seen either of them, then we're done. We died. So we have to return the distance that currently up to. Otherwise, seen is set to true, and seen is just whether they're in a group yet. So it actually didn't matter which group they're in. What matters is whether they're in a group. So we just say it's true, and if we've already seen them, then we print the distance. Yeah. And note that somewhere along the way in this for loop, just because there's so many pairs, we're eventually going to get a collision. And so that's why I don't need to have anything underneath. In fact, we're probably going to, you probably show that you can like, get a collision within like the first n or n over 2 pairs, but whatever, you can just do the whole for loop. Okay. Have there been any questions on that? Any questions about the implementation or the solution or the proof or anything? Feel free to let me know. Yeah, it's a good question. So yeah, this is just a detail on how the solution works. So what we said was if 2 people were in the same group, I mean, so if either person was in a group already, then we died. So like, for example, I think one of the sample cases, or many of the sample cases, we had it like this. So these 2 people were grouped first, and then once they were grouped, the next pair that we're going to cover is this one because it's the next smallest distance. And since this one's in a group, we can't join that edge. So yeah, even though this guy's not in the group yet, we can't form a group out of these 2 people. So we have to return that distance there. So, I've been a bit messy with all the pairs, but I think that pretty much had to be done. And so that just exits the main function. Okay. Oh, yeah, I guess we can wait 30 seconds or a minute for any other questions. Otherwise, I can move on to the next problem.
All right. Let's move on to the next problem, which will be F. So again, same link from before. We'll look at problem F. You should be able to see my screen here. Flavors galore. So in this problem, you want to make tall ice cream scoops. You want to have as many scoops of ice cream as you can. She always eats ice cream from top down, and she does not mind if there are multiple scoops of the same flavor in the tower. So you can repeat flavors. You can have one ice cream flavor multiple times. That's allowed. However, there are some rules. There are only some flavors are allowed to be directly on top of other flavors. So you have some acceptable combinations. So you could have like, chocolate, chocolate and like vanilla. This would mean that X is on top of, we can have chocolate on top of vanilla, for example. So vanilla chocolate is allowed, but chocolate vanilla is not allowed because in this case, vanilla is not on top of chocolate. Chocolates are on top of vanilla. And you're given a bunch of these pairings of the form X and Y, where that means flavor X is acceptable on top of flavor Y. And the question is, using this, what is the tallest tower you can make? Or can you make an infinite tower? infinite scooped ice cream. That'd be quite a nice ice cream. Take a while to finish though. So in this case, for example, you're allowed to put 1 on top of 2. So the flavors are just numbers. They're not, 1 could be chocolate, 2 could be vanilla, 3 could be strawberry, for example. There are up to F equals 500,000 different flavors, numbered from 1 to F. Additionally, there are some number P up to 100,000 valid flavor pairs. So for example, you could be allowed, in this case, you can have 1 on top of 2, 2 on top of 3, and 3 on top of 1. So in that case, like 3, 2, 1, 3, 2, 1, etc. is allowed because you can have 3, and then 2 is allowed on top of 3, and then 1 is allowed on top of 2, like this, and then 3 on top of 1. And you can repeat forever. So you can have the combination 3, 2, 1, 3, 2, 1, 3, 2, 1, 3, 2, 1 forever. And if it's infinite, you output -1. In our second case here, we can have 1 on top of 2 and 2 on top of 3. So we're allowed to have 3, 2, 1, like this. But we can't have any more than that. We could obviously have just a 1 scoop ice cream or a 2 scoop ice cream, but the biggest ice cream we can have is a 3 scoop one with 3, 2, 1. We can't beat that. You could also have the case where, let's say, we had a case where 3, 1, 1, 1. In this case, we have 3 flavors. In fact, we have 2, 2 here even. In this case, we have 3 flavors, 1, 2, and 3. We can have 1 and 3 alone, but the only allowed stack, we can have 2 on top of 2. So we can have infinite ice cream of just all flavor 2. That's also allowed. Okay, hopefully the problem makes sense. We just are given a bunch of pairs of which flavors are allowed directly on top of other flavors. So by directly, let's say you're allowed to have like 3, 2, 1. Even if 1, it doesn't matter whether 1 can go on top of 3. All that matters is like adjacent 1. So can 1 go on top of 2, and can 2 go on top of 3? That's all that matters when creating the 1, 2, 3 ordering. So as always, I'll give about a minute to think about it and share any ideas, and then I will discuss and like speak up if you're confused or if you have any ideas. I'll give another 30 seconds. Okay. So as written, it's quite hard to think of how we would make ice cream scoop. We could just like try. We could like we could put 1 at the bottom, and then see what can we put on top of 1. But there can be many options, and there's no immediate way, I think, to think about how we can build ice creams. But in problems like this, it's good to be able to come up with a way to visualize what our options look like. And what structure can we use to visualize this in order to like pictorially represent our options and perhaps think about it a bit closer. This just describes like a directed graph. So in this case, we have like, first one we have a graph that's like 1, an edge to 2, an edge to 3, an edge to 1. In the second case, we have 1 with an edge to 2 and 2 with an edge to 3. And on this graph, an ice cream is allowed if it forms a path, because we can have like 1, 2, 3 is a valid ice cream because like 1 can go on top of 2 and 2 can go on top of 3. So the reverse order, like 3, 2, 1, like 1, 2, 3 from top to bottom is a valid ice cream. In this first case, we can like loop around it as many times as we want, like this. You know, we can just keep, we can go like, you know, 1 loop, then a second one, then a third one, and we get the ice cream like 1, 2, 3, 1, 2, 3, and go on forever. A more complicated input, let's say we had the input, which was 5. We could have like 1 on top of 3, 2 on top of 5, 3 on top of 2, 2 on top of 1, like this, and maybe 4 on top of 5. As a graph, that would look like edge from 1 to 3, an edge from 2 to 5, an edge from 3 to 2, an edge from 2 to 1, an edge from 4 to 5. So we got this case here, and maybe we add another, we can add another one here. Let's say we also had 3, 5, like this, 3, 5, an edge from 3 to 5 like this. This could be, if we were given this input, so the input would be 5 followed by, well, there are 6 connections. There are 6, in fact, there's 5 followed by 6 different connections like this. I drew 3 twice, didn't I? Yeah, I drew 3 twice. That's why it looks weird. We have 2 to 3. We have like this. I'm gonna get rid of this 3, 2 connection, and we're gonna add. I'm gonna modify it a bit. Sorry, and I'm gonna put a 6 over here instead. Make it a bit more. And we'll have 6, 2 here instead of 3, 2. We'll have 6, 2. So hopefully I do this correctly. Hope so at least. If I didn't, whatever. But this is our graph. Let's say from this input we convert to this graph, assuming I didn't make a mistake. And so now it's not easy to visualize because an ice cream is just a path on this graph. And so the biggest ice cream is the biggest path. And what can we do? Well, we can do this path has 4 things on it. This path here has 5 things on it. And it seems that that path there will be the biggest one we can do. So on this input here, the answer will be 5 because the biggest ice cream we can make is of size 5. And that ice cream is precisely the ice cream 5, 3, 1, 2, 6. Because 5 can be on top of 3, that's from here. 3 can be on top of 1, that's from here. 1 and 2, that can be like here. And 2 and 6 from here. So we have all of our connections are legal. And so we get this ice cream here, which has 5 scoops on it, which is the maximum in this case. So using our graph here, in what situation is the answer infinite? So infinite when we output -1. What condition must be true for the answer to be infinite or -1 in terms of our graph? A loop. Yep, if we have a loop. Have a loop or a cycle mean the same thing. Then we can do infinite. Let's go around it as much as we want. Just keep going around infinite. So I want to check whether our graph has a cycle or a loop. So we can check this with what's known as the depth first search, a DFS. We looked at that in our last week workshop. If you're confused about how to find cycles, let me know and I can go over it, but we just want to check, does a cycle exist? Yeah, again, if you're confused about, if you want to know more about how to check if there's a cycle, let me know. But otherwise, we just can do a DFS to check, is there a cycle? Now, if there is a cycle, then the answer is -1. So check for a cycle. If there is a cycle, output -1. If there is not a cycle, we want to find the longest path. Now, if there is no cycle, what structure that, oh, I mean, this is a name for it. I can just give you the name. It's called a directed acyclic graph, or DAG, sometimes abbreviated as. So if there's no cycle, we have a directed means every edge has direction. So like the edges are one-way edges, which they are. Acyclic means no cycle, and graph is just the structure we have here. So directed acyclic graph, a DAG, is what we have. This is a DAG, for example. There's no cycle in it. And the problem is now the longest path in a DAG. Now, we have, 15 minutes left till 6 o'clock. So I guess a few options. One option is I just go over this conceptually. Another option is I give you code. Do you have a preference whether I just provide conceptual how it works or whether I provide code? No preference? In that case, I'll probably provide just a conceptual explanation. If there is demand, or maybe a little bit of conceptual, yep. Then if no one else chimes in, I'll just provide conceptual. Give myself a blank page though to work on. It's a bit nicer. So we want to find the longest path in a DAG. So first of all, check one, do we have a cycle? And check two. Check one, do we have a cycle? Check two. Longest path. The first check, do we have a cycle? So in this directed case, it's a bit more complicated than the undirected case. But the idea is we can do a depth first search. So this graph here, a depth first search starting at 1. Go from 1 to 3 to 5. Look at this. Depth first search 1 would look like this. And we just kind of keep walking around until we see, and then unless we see a cycle. So unless we go back on any previously visited edges on our current path. So we keep track of all the vertices on our current path. And if we ever loop back to something we've already seen, then that means we've encountered a cycle. So in our DFS, we just keep an array, like a Boolean array of like on path. What we've seen, like an array of, is this thing on our path or not? And as we start with DFS starting from 1, we DFS to 3 and to 5, and we mark whether each of them is on our current path. And if we ever find a new edge that goes to something on our path already, then we've found a cycle. Now, one nuance of this DFS is we're answering more than one DFS, because obviously 1 will only visit 1, 3, and 5, but there might be a cycle involving 6, 2, and 4. So we do a DFS starting at every vertice, except we put the vertices into 3 categories. We have unseen vertices, we have on-path vertices, and we have seen vertices that aren't on a path. So if we've never seen, if our DFS hasn't visited a vertice before, it's unseen. If our DFS has visited a vertice, but is currently like, if it's on the recursion stack, then it's on path. If we've visited the vertice and then our DFS has returned for that, we call it seen. And the one thing is, if we ever DFS to a seen vertice again, then we know it's not in a cycle, because if it was in a cycle, it would have found the cycle. And so our DFS looks something like, if we've seen it, return, then we mark it as on path. Then for every edge B, if B is on the path, then we've found a cycle. Otherwise, if it's not on a cycle, we just DFS to B. And then at the end, we say we're not on the path anymore. So on path, A is false. And at the very end, we set seen A to be true. So we set on path to be true when we start, and to be false at the end. When we set on path A to be false, we set seen A to be true. And so this DFS function, very rough code, kind of guarantee we'll find any cycles if there are any. It won't, yeah, that'll detect that there is a cycle. If there's a cycle, we output -1 and we're done. Okay, there's no cycle now. Want to find the longest path in the DAG. This is actually kind of a fairly well-known and classic problem, but and there are actually quite a number of solutions to it. I will describe, I guess, 2 solutions. There's a dynamic programming solution and also a greedy solution. We have our DAG, like here, I'll draw it out. Here we have 6 to 2 to 1, 1 to 3, 3 to 5, 2 to 5, and 4 to 5. This is our graph here, and we define dp of A to be the longest path starting at A. And how do we compute dp of A? Well, this is just precisely equal to the maximum of dpb, where AB is an edge, where A to B is an edge, plus 1. 1 plus the maximum. So as an example, dp of 5 is 1. dp of 3 is, well, there's only 1 edge out of 3, and that's to 5. So we get that value and add 1, we get 2. We get 3 here. Then for 2, it's the maximum of 3 and 1, our 2 children, plus 1. So we get 3 plus 1 is 4. So we get 4. Here we get 5, and here we get 2. This will find the longest path starting at each of the vertices given. And this is computed in linear time, because at order n states in our dynamic programming solution and order 1 recurrence. So an order n solution to find the length of the longest path in the DAG. And that's precisely the answer. Now, another longest path in DAG solution is a greedy one. Or I guess it still computes DP, it computes a DP greedily. So I guess it's still kind of a DP solution, but it kind of computes a graph, it computes the cycle one thing at a time. We're going to compute it from the top down. Yeah, still ends up being quite similar to DP actually. But we first of all, we get all the vertices which have nothing coming into them. So that's this one, this one. These two have no edges going into them. Now, we might as well start our longest path at one of these two vertices. Like we might as well start it somewhere with nothing coming into it. Because if we want to start it here instead, we can make it longer by including the two. So we want to start it at a vertice which has no incoming edges. And so we set the length of all of these, longest path. We now find the longest path ending at each node. So we're going to find the longest path ending. And we get 1, like that. We then, conceptually at least, delete these two edges, the edges leaving these vertices. We conceptually delete them like this. We then look at our new graph with these two edges deleted, and we find, okay, which vertices have no incoming edges? That's going to be just this one here, in fact. Just our 2 over here. Everything else still has at least 1 incoming edge, but because we deleted these 2 edges from 4 to 5 and 6 to 2, the 2 has no incoming edges. And so what's the longest path that ends at this 2? Well, what we do is we look at every edge going into it that was deleted. So look at this edge here. Out of all the incoming edges, we find the longest path, that's 1. And then we add 1 to it, so we get 2. And then we delete all edges that leave this vertices. We go delete, delete. We now find anything with no incoming edges. That's this 1 here. What's the longest path going into it? That's 2. Add 1, we get 3. We now delete all edges going out of it like this. So we go delete. Anything with no incoming edges, that's a 3 here. What's the biggest path that goes into it? That's length 3. Add 1, we get 4. The longest path that ends here is 4. Finally, for our 5, we delete this edge here. Now the 5 has no incoming edges. We then go, for everything coming into it, what's the biggest path? Well, we have the 1, the 4, and the 2. The biggest is the 4. We then add 1 and we get 5. And so the longest path ending here is 5, which means the longest path is 5. And so our answer will be 5. And that's a second way, which is actually very similar to our DP. We're just not doing recursively, we're doing it iteratively instead, to find the longest path in the DAG. And so our algorithm is step 1, is there a cycle? That's a DFS. Step 2, find the longest path using either method we described before. The constraints are clear here. The constraints are up to 100,000, but our solution, if done fast, is order F plus P. Because checking if there's a cycle is order F plus P, that's a complexity of a DFS. Then our algorithms to find the longest path, our DP solution is order F plus P. Our second solution, it depends how fast we do it, but if we have good bookkeeping, we can do an order F plus P too. Although if we are a bit if we loop through each time to find the things with no incoming edges, it's too slow. So probably the first solution, the recursive DP solution, is probably a better way to do it. Because the second solution where we delete edges we look at all the edges with no incoming, all the vertices with no incoming edges, while conceptually that's quite nice, finding those vertices can be too slow. But it really depends how, like, you can do it more efficiently if whenever you delete an edge, you check. So if you delete an edge from like A to B, you check, is this the last remaining edge to B? And if it is, then you add B to a list of things with no incoming edges, like that. If you do that, then your solution will be fast enough using in both cases. Does that make sense? I did quite a high level overview. So if you're confused about any of the details, please let me know and I'll explain them in some more detail. Okay, we're at 5:55 now, so I don't think we'll have time to another problem unless Isaiah really wants to do it, because
No.
no, yeah, because we'll go, it takes like what, half an hour to do a problem. So divisionals are tomorrow for anyone doing it. Good luck. If you have any last questions about either this problem, any other problem we covered today, or any other question pertaining to divisionals, let us know now. Also next week, so next Friday, we'll run a workshop where we'll go over divisionals problems and we'll go over the solutions to some of the problems from a divisional contest tomorrow. So if you're keen to, after doing the contest tomorrow, if you're keen to hear some of the solutions, some of the harder problems from divisionals, then we'll run a workshop for that next week.